We're going to talk about distributed storage today, and we're going to focus on some of the key issues using examples. We're going to get into NFS and AFS. These topics, AFS and NFS, are actually covered more deeply in the book, but I want to give you an overview of what I think is important and what to think about when you're thinking about comparing distributed storage systems. Some of these issues, if you're going to be doing storage as one of your projects, some of the issues that are brought up here will be ones that you should definitely focus on in your body of your work. A simple answer is just it's storage that can be shared throughout a network. And some simple examples of that are the Windows file sharing that we had talked about earlier. FTP is another one. There's a lot more sophisticated examples like file systems, distributed file systems like NFS, AFS, and even something like distributed shared memory, which we're not going to get into, is a good example of distributed storage. There's a chapter on distributed shared memory. It's one of the last ones in the book. It's pretty interesting stuff because there's a very different set of requirements for that versus what we're going to talk about today mostly, which is distributed file storage. Some of the key objectives, there's a lot more objectives here. You want speed, right? Because this file access or memory access, storage access can be a big bottleneck in your system. You want availability. Thing that you don't want is for, when a program needs some bits, for them not to be there. Consistency. This is going to be a very interesting objective because this is hard to get. This is one of the harder ones to get. But we've talked about consistency before. It becomes even more difficult when you have lots of people sharing or doing updates. Fault tolerance. If you take a server off, if you just unplug a server or take it offline, just asynchronously, it should be able to come back up in a state that's consistent. Security. Security becomes an issue when you move the files off your local disk, off to somewhere else where you can't control who has physical access to the machine. And transparency is one that's a bit interesting. Transparency is interesting because ideally you want to be able to access your storage as if it was local. But on the other hand, there's some end-to-end arguments as to why you wouldn't want that. And we'll see as an example in NFS later as to how they deal with that. So when you think about distributed file storage, these are typically implemented as these big dedicated file servers. And in order to get speed, they're highly optimized. In particular, their disk architectures, subsystems optimized, and their network subsystems optimized. So they'll have RAIDs, like a lot of level 1 RAIDs. They'll have huge hot file caches and high-performance Ethernet cards. So, I mean, I remember when I first saw one of these things about 10 years ago. There's these big boxes. They have tons of disks in them, and they have an ungodly amount of memory in them to buffer the files as they come out. And the Ethernet cards typically are ones that try to do as much processing on their own and leave the CPU from having to do any kind of processing. So sometimes you can imagine. I don't know if they do this, but you can imagine some of the layers. Network layers being pushed down into hardware if you want to, for example, build a dedicated file server that's going to be using IP all the time, and it's going to be using IP, then there's no reason why you can't shove that down into hardware. Now these file servers will manage the bits, and to get speed, you can actually replicate them so that they can serve in parallel. But more importantly, you want to replicate them for availability. So if one goes down, there's still another one that can serve you the file. And it also gives you some amount of fault tolerance. So if one of them goes down, and let's say you're writing, and both of them are trying to write back to their replicas, and one of them goes down, the other one will still have the information. Now, the hard part here is when you replicate, you get all these good things. You get speed, availability, some more fault tolerance. But the really hard part is that consistency then becomes difficult. In fact, it becomes very difficult. And this is why you see a lot of different types of file systems out there. We're talking about 2 today. There's going to be one that you're going to read about, the Echo. But there's a lot of literature about lots of different types of ways of doing this. And it's the key trade-off here in distributed file storage is how do you get this replication but still manage to get some level of consistency. This becomes a huge issue, you can imagine, in distributed memory. Because file storage, as we'll see, you can probably get away with a little here and there. But if you have distributed memory, I mean, that you don't want to completely bring a machine down by having inconsistent versions of bits. Can
you explain again consistency with regards to file storage?
Yeah. So if you replicate, and this is what we'll start seeing in all of these. If you have just one file server with the files, then anyone who writes to this, right? Then there's one place where you can manage all the updates to this file, right? So that's great because there's one place. It's still an issue, as we'll see, but there's only one. Now imagine that you have lots of them. So if you update this one, then that update needs to propagate to these. But if they're connected via an unreliable network, which most networks aren't completely reliable, especially if you distribute these copies throughout the internet, then what happens if you update this one, there's some network problem and someone else accesses that same file over here? Well, then here's one version of the file and here's another version of the file, and guess what? You got the older version of the file because the newer version of the file is trying to propagate through here. So that type of writing is one of the things that makes this very hard. Is once you start replicating, it's great if these are all read-only, right? Because if these are read-only files, then hey, go for it. But as soon as you introduce writes, then the consistency issue becomes big.
Are writes usually done in a sequential timeline? It's not one write and then it branches out to all four at the same time. Say you have 4 files.
Well, in designing these, that's one of the parameters you have to decide is how things get propagated. So you guys remember in Grapevine, there is a propagation method when they do writes to propagate data out, right? So Grapevine is in essence distributed file storage, in which they have all this naming that they use that file storage represents, but that's one mechanism, and we'll see others today. Security is a big issue. You can imagine that people will want, as long as your files are stored out there somewhere, people are going to want to find them. We talked about the Windows file security issue, that there's this new program that goes out and finds all the Windows shares out there that are available and puts them into some directory, so you can just click and onto someone else's hard drive. Well, this is a disaster for people who have sensitive information. The interesting thing about security is you can actually build it in at different layers. So you can imagine at one layer, you can say, oh, at the highest layer, I'm going to encrypt all my files. And the newest version of NT 2000 has an encrypted file system option that you can use, so that even if someone does get access to it, they'll just get a bunch of bits that they shouldn't be able to decode. What's the trade-off with encrypting all your files? Speed. You have to decrypt them all. So let's say that speed becomes too much of an issue for you. Well, there's other things you can do. There's access control lists, which we talked about before. So every file or directory will have some access control list which says who gets what kind of access, when, and why. It can be simpler than that. Tickets. So you can hand out tickets to say, this is what Kerberos does, hand out tickets and say, you can have access to this, you can have access to that, you can have access to that. And even simple passwords, which is what you would use in the Windows file sharing case. The key here is that as you push the security down, then more people have to pay that cost. The fault tolerance piece, one of the things you really want to do to get around that is to make the servers as much as you can be stateless. By stateless, it means that they don't have any volatile state that will, because the volatile state dies when you unplug it or dies when the machine crashes. So the more stateless it is, then the easier recovery will be when it comes back up. And one of the ways that you can do that is to use, we'll cover this more, transactions or logging. So imagine that when a file comes in, you immediately log that data's come in, and you put it in somewhere where it's in a non-volatile memory, so something like a disk, and then you send back a response saying, okay, it's saved, and then you start actually writing it back. If the machine goes down at some point, you'll still have that record of it in a place that won't go away when the power gets cut off. We'll get into more of the semantics and how that works and different types of logging and transactions over the next few days. I think for those of you who haven't, you've probably used it. It's a network file system developed by Sun. It's been around for ages. It's based on RPC. We had a lecture on RPC earlier. It's flexible, so you can, in terms of implementation, you can put it on top of UDP or TCP, and it's transparent in the sense that it builds it. When you use a computer that's using NFS, you have what's called a virtual file system that makes the fact that files are remotely being accessed transparent to you as the user and to processes, to an extent, as we'll see.
How can you build it on top of UDP and have any idea of what you sent got there? I mean, if you ask for a change to a file.
If you can build in some extra functionality. You don't need the full TCP functionality, so you can just build some. Yeah, you can just build something on top. Build in what you need on top of that. So in NFS, files are identified by file handles. So usually in typical Unix, you just have files are identified by what are called inodes, which just correspond to a particular, it's a one-to-one correspondence between a file and this ID. When you're working with NFS, you actually have these file handles, and they consist of three things. One is an inode. Another thing is called an inode generation number. And then you have a file system identifier. Now, are there any Unix gurus around here that knows why we need these two things here to identify a particular file on a given file system instead of just the inode? So if you're using in Unix, when you create a new file, you get back an inode, and this thing corresponds to that file. But when you delete that file, the inodes get reused. So the thing that you don't want to be in a case when an inode you think corresponds to one thing, but then it actually ends up corresponding to another because at some point that file got deleted and the inode got reused. So what happens is that anytime an inode gets reused, when you assign the next file handle that's using that same inode, you increment this inode generation number. So that way you always have this plus this always gives you something that's unique. Now this part here, as you can imagine, has identification information as to where that file is stored. So is it stored on my local server here? Is it stored on my remote server? And which one is it? So once you know where it's stored, then you can use this to get at that actual file. When you're programming this layer, this is everything's everything uses file handles. All the system calls use file handles. And if you look in the book, they talk about a sample interface, and they show you how you manage the files through file handles. Yes.
You said if you delete that file, right? Then if you redistributed that same inode to a new file, it's still unique because there's only that inode only represents the
Yeah.
new file.
So imagine that I had a file handle, right? So let's think of this situation. I have a file handle, and then someone else out there deletes that file, and then suppose we didn't have this inode generation number, right? So let's say we have a server, we have a file, and it has an inode number on it, and that corresponds to some MP3 file, right? And then someone on that, the system, and here you are over here, And occasionally you go out and grab that file and you're playing it. Now imagine that someone on the system administrator on that system says, oh, this is bad. If someone's filling up my system with MP3s, I'm going to delete that file, and I'm going to create a new, and in the process later on when things are created, like someone's quiz solutions are created with that same inode. Now the next time you go to get your MP3, instead you're going to get the quiz solutions back, because that is switched. So if you have this inode generation number, then when you go back here, it's going to say, oh, that file's been deleted because the inode generation number is going to be different from this file and this file. When NFS is a client-server architecture, so you have clients and then you have servers with the files. And the way that clients access these files is what's called they're mounted on the local file system. So as you know, I think you guys know that this whole directory structure, right? There's slash, and you can have slash dev, slash, etc. You can have, right? And it's a hierarchy that the file system is treated as a hierarchical structure. One of the things that you can do is, what some people do is they'll have a directory called /mount. And then in here, they'll do what's called mounting a file system. And say over here you had something called MP3s. And then you had, Madonna, Ricky Martin, all that. So what you could do is, when the client wants access to this directory, what it does is it'll send a request out to mount this directory locally. So what will happen is from the client, you'll be able to say cd into /mount /mp3s / Ricky Martin, and what the operating system will do for you is make sure that when you cd over here, that it's grabbing the data off of the server that you're requesting. So if it's just CD, you're going to get the directory information. If you start saying play this file, it's going to start sucking over the data that actually corresponds to that MP3. To you, this is going to seem like a local file because it's mounted transparently like this into the file system. And the thing you may, if you're watching carefully, if the server's loaded, it's not going to be totally transparent. I don't know if you guys have ever seen this, but you'll type CD, something like that, and then it'll take a little bit longer than it usually does, like maybe a second or two. That could be because of the delay, because it's actually getting it from somewhere else. Yes?
Did you just say there's two ways to call it, but the data is only in one spot?
The data's over here.
Right.
And so what happens is when you say CD into /mount /mp3 / this, what'll happen is that if this is, there's a protocol for you to auto-mount NFS shares. So what it'll do is it'll say, oh, okay, I need to get this from this server over here. And it'll grab this, it'll grab the directory structure, it'll suck this back over here and allow you to CD into that directory. And then when you say, give me this Ricky Martin file, MP3, it'll go back to the server and grab that data and then start processing it for you.
I didn't get the difference between the two steps. And is that like two remote procedure calls? Or?
Yeah, it would be implemented in 2 or more remote procedure calls, but the difference here is that just going into a directory doesn't require you grabbing all the files from that directory.
So the first time you just go into it?
Yeah, if you type in CD, that. Okay. But if you say something like, if you say play, and then you just say mumble, then it grabs. That's when it grabs the data. So in essence, what NFS tries to do is to say, let me grab the data only when you're asking for it, because otherwise you're transferring a bunch of stuff and network performance and all that. So there's directory information, there's file information.
If you connected to more than one server, would you need some identification for which server?
Yeah, and that's why you have these file system IDs. So a file handle like this will say, oh, this is on this system here. Now, the way, if you're a server, the way that you allow one of your mounts to be, one of your local file systems to be exported, is there's a directory called etc. exports. And anything that you put in there, you can put in some parameters like whether it's read only or read write, things like that. When you put something in there, that allows NFS clients to be able to access those files. So in the etc. exports, you can have something like MP3s. And this actually can be, suppose that you have this on /local/MP3s. You can say, here's can I erase this? Okay. March Madness. So what you can say in this file is you can say /local/MP3s. I'm going to export that as MP3s, and I don't remember the exact file format, but you can say it's read only. So you can give something like this. And so when the client comes over and says, I want to access the mount called MP3s, it'll look over here and say, oh, that's on my local drive, which is local/MP3s. And so I'm going to export that, but I'm only going to do it read-only. So someone can't write to it.
So then like in a law firm, they have like iManage so that people want to share the documents. And usually it's just considered you're checking out the document. Where's the equivalent of the checking it out? Write to it.
Yeah, in NFS, there isn't an idea of checking out a document.
Oh, there is.
So what will happen is you'll just tell someone, oh, this document is in /doc/case5324/deposition. And what will happen is that anyone can go to that server and grab that file into their buffer. Now, what happens if someone tries to write that file? Right, then that's when you start getting into these issues. Well, what happens if like two people are logged into one Unix system, and the same two people bring that file into their buffer, into separate Emacs buffers? What happens when one person tries to write that file? Pardon? Unix?
Emacs will say something.
The other person's Emacs will tell you something the next time you try to modify it. It'll say this file's been modified. But guess what? What are the bits on the disk at that point? It's the new bits, right? Those have been written. And that's why Emacs knows it can look at the modification date and say someone else has written it. So Unix doesn't give you any real sense of checking things out, and neither does NFS. Now, there are two types of mounts that you can do. One is called a hard mount. And what a hard mount means is that whenever there's any operation that accesses the files or directories on that hard mount, it's a blocking operation. So what does blocking mean? Talked about it before.
Wait for it to complete.
Yes. You have to, the process just stops and waits for that read or write or whatever type of operation it is to complete. That's blocking. And that's typically that's what the standard semantics are when you do for most programs on Unix, is that they'll assume that it's a local drive, that if the data isn't there, it's just going to wait for it, and typically the data appears very quickly because it's a local drive. If it's not a local, now in the case that it's non-local, there can be substantial delays that are added depending on the load of the network and the load on the file servers. So what was the thing that NFS did? We'll say, okay, well, there's hard mounts, and then we'll make soft mounts too. And what a soft mount is whenever you do a read or write or any kind of operation, file system operation, to something that's soft mounted, there can be something like a timeout or a failure condition that comes back, and it's a non-blocking operation. So that means that when you do that, it can actually come back, the procedure that you call the read or write, whatever it might be, can come back and tell you failed or timed out, or there's some issue here. Now that's great in the sense that now you can write applications that don't depend on this link being there. They can do something graceful, like come back and tell you, sorry, this file, this file isn't available. Problem here is that isn't backwards compatible, which is that there can be, if you have a program that doesn't know about soft mounts, it can go off, and when it gets this nice exception back saying unavailable, it might just barf and say, I don't know what that means, and give you a core dump or do something horrible to you. So that's, I mean, unfortunately, it's not, the soft mounting isn't backwards compatible. The hard mounting is backwards compatible because that's the typical semantics, but then you don't get the nice sense of being able to recover from failures. So there's a trade-off that was made.
The directory is stored as a file on my local machine, but it could be out of date. If I ask for the existence of a particular Ricky Martin track, could I be told, yes, it exists, but then when I try to access it from the actual server, it's no longer there?
Yeah, absolutely.
So that could make programs bark because they're not used to that kind of behavior.
Well, actually, but that can happen even on a Unix system. Like if, in this case, if we were two people writing to the same file, right, and then one blows it away, right, just
after I check for the existence of
yeah, all of a sudden it's not there anymore. So what are some of the things that you can do to improve performance on NFS? So what are the performance issues? Well, one of them is you want a lot of speed back and forth. Well, locally what you do, and so the big answer is usually you do caching. Caching is the thing. All file systems try to do some amount of caching to improve performance. Now you guys talked some about caching before, right? In the how computers work course. Okay, so you know what caching is. And we talked about it some when we were discussing the virtual memory, right? Registers cached in L1 cache, cached in L2 cache, cached in disk. So what file servers or clients typically do, or most computers, is they'll do some kind of read caching. So they'll have, get this. You have the disks. And when you read a file in, what the OS does is it has this big, in essence, piece of memory that it calls the cache. And when you ask for a file, it can put it in here, Ricky Martin track 1. And this is all memory. You can have, Madonna track 1. And what the operating system will do is it'll take that file and put all or pieces of it into this cache, and then when your application up here, Sonic, asks for it, it's going to be reading it from memory instead of reading it from the disk. So that's good because the disk is this physical thing that takes a while to get to the right sector and all this, whereas memory you can just access it randomly, do random access very quickly to it. Now, one of the things that you can use here is what's called read-ahead caching, which is that if you ask for byte number 1 of RM1, what you'll get back is the next 8K of RM1 into the cache. And the reason you do read-ahead is because something like the assumption here is that when you read 1 byte, you're probably going to ask for a lot of the bytes subsequently, and in practice that tends to be the case. So that helps you optimize the disk access. Now another thing that's used is what's called write caching, which is suppose that I'm making changes to a file. What happens is that you've read that file in, and then you have an Emacs buffer and you're making changes and changes and changes. Why write every change back whenever you make it? So when you type another letter in, you shouldn't have to write that back. Even when you're saving things, why write it back then? Instead, save all of the changes in memory in this cache, and then at some point later on, shoot them out back to disk. And that's called write behind or delayed write caching. And again, the reason is that you'd much rather be interacting with memory when you're reading or writing than you want to be with the disks, because this is a lot slower. So this is great if you have local file systems. Why? Because you have, the OS. You have one OS file cache that's doing all this stuff here, and everyone's, the only issues you have are if multiple people are logged into the same machine there. But let's think about what happens when you're going to something like NFS. Well, when you're going to something like NFS, the file server, imagine that the file server wants to do some kind of read caching. Well, that makes sense, right? You can pull stuff into memory like this. And if 5 people are asking for the same file, that's great because you don't have to go back to disk to get it. You can just serve it from your file cache. And that's actually one of the things that adds a lot of performance, because it tends to be that the same files are being used more often than the rest of than 100% of the files. The same 5% of the files are typically the ones that are most being used, and I'm picking those numbers just as an example. But the problem with there's a problem with write caching. One of the huge problems with write caching is, imagine that I've got some Emacs buffer, and I have some file that I've mounted from this file server, and I'm sending a bunch of changes to it. I say save buffer, and so then that change goes over, and then imagine my file server caches that save in its cache in memory, and then I just say write it. I save my buffer again, and I save my buffer again, and it's all in memory. Well, that's good because the file server doesn't have to go to disk to write all those saves out. But what happens if someone unplugs the file server, or if it crashes or dies? What happens to all of these writes? Bye-bye. They're gone. So now you think you've saved all your work, and it's gone. It's blown away. And in fact, I remember when I was first using NFS, this bit me a couple times. And I'm not sure why this stuff wasn't saved, but I remember saving stuff and exiting Emacs and then coming back the next day, and it was some old-looking version of things. It was horrible. But this is one of the reasons why delayed write caching can be dangerous on file servers. So there's a couple options that you can use to try to get around that consistency issue. One is to just use write-through caching, which in essence is not using the cache. What happens is that whenever you write, it immediately it treats the cache as like an instant buffer as a buffer that instantly needs to be dumped. So it'll bring the write in, and boom, it writes it immediately, and it sends back an acknowledgement. It doesn't send back an acknowledgement until that write has completed. So then when your program receives the acknowledgement that the write is completed, then, for example, in Emacs, your little 2 stars will go away, and you'll know that it's there. So that way, when you save, as long as Emacs told you, or the client told you that it's done because it received an acknowledgement, then you can rest assured that it's done. Now the problem with that is that it can be a performance bottleneck. If you're writing to a file, if it's just one person writing to a file, then you have to wait for that file server to handle that request. So if you're issuing lots of writes, then each one is going to have to wait. Whereas if you're doing them locally like this, they would just go boom, 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 and change right here, and then later on they'd be written. Over here now, each write incurs the round-trip delay, or at least one round-trip delay time, in addition to dealing with the load on the file server. So what's another option? Well, one other option that's been added to NFS to get around that is that the client tells the file server explicitly when to clear that cache. So what you can do is do a lot of writes, boom, 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 boom. They get written into a cache, and then the client will say something like commit. And when the file server gets the commit, it takes all those writes that have come to that file, and it saves them on disk. And then it gives an acknowledgement back. So at that point, the client can be sure once it gets that acknowledgement back that the files have actually been written. But then what does that do? What's the trade-off there? Well, you get this window of potential disaster. And the trade-off that you get, the reason you get that is for performance, because now you can do lots of writes. Question?
No, so when the system crashes, you know exactly what stuff you've lost.
Yeah.
Like instantly.
Yeah, you'll know it's the stuff that you haven't committed. It's the stuff you haven't committed, yes.
I mean, the bigger problem strikes me, not so much if the server dies, but if you take a file, edit it, but someone else accessed that file at the same time. So once you've sent in your changes, then he sent. I mean, this is sort of like CVS, but if it doesn't have the backup mechanisms of CVS, then he would just overwrite everything you change.
Yeah, and that's the same thing as what happens if 2 people are accessing the same file on a local machine. Like if I'm making my changes, they're going to be written to the local cache, right? But when they make their changes, they'll overwrite what's in the local cache. So you're both and because the local cache in essence has the current working copy of the file. So it's the same issue that you have with coordination. Question? No? Okay. Yes.
You say that right behind is a good idea for local machines, but not for remote servers because they can die and then your work will be lost. Presumably the assumption is that that kind of server will die much more often than your local machine ever would otherwise.
Yeah, there's that assumption. There's also the assumption that the round-trip delay time is higher so that it actually affects you. So right behind, if you have the round-trip delay time between a local process and memory is it's very fast. Over here you can have some longer round-trip delay time. If it turns out that this file server is on your local subnet, it might not be as big of an issue because that can be very fast communication back and forth. But if this file server is on the other side of the, if you're trying to do something on the other side of the US, then you can have lots of milliseconds of delay, and then the performance bottleneck can bite you.
I wasn't talking about the performance bottleneck. I was talking about the reason why right behind is a bad idea.
Well, right behind, one of the reasons it's a bad idea is because of performance over here. Because, I'm sorry, because of fault tolerance. That's what you're getting at. Okay.
So my question was, why is that necessarily going to be worse when you're working on a network than when you're just working locally?
Right. So there's a couple reasons. One is that, as we talked about before, the file system can go down.
Right.
Another one is that if the network's unreliable, then some of your packets may not make it over to the file system. So you can lose packets, and remember the IP doesn't guarantee, it says it's best efforts. So if there happens to be congestion along the way, those packets can get dropped. And NFS, remember how we talked about the two generals problem, which is that there's no guarantee that right? So you can have issues where the packets don't end up making it. And that might have been one of the reasons why my files disappeared, because even though it said that it wrote them, maybe some packets disappeared and it thought it wrote them, but it can't.
That's going to be a problem in any case.
Yeah, yeah.
Not specifically a problem with the right behind.
The reason it's a problem with the right behind is because if you say you don't use the right behind, say you just say you do right through caching, then anytime I send something over, right, it's going to write it, and then it's going to send me an acknowledgement back saying I just wrote this stuff. So if I'm doing right behind and I say write this, right, then it puts it in a cache, and it doesn't tell me I wrote this stuff because I don't know at that point. It doesn't guarantee that stuff is over here in more permanent storage.
So it's just a very general matter of less reliability.
That's right. So now we get to the issue of availability. So here we have, great, NFS, here's how it works. But how do we make sure that our file servers are more available? And this is important. This is very important because you don't want to be in a position where you log in and you can't access your files. That would really be bad. So one of the ways that you can get around that is, for example, what Grapevine did is introduce the idea of replication. So you have the same data replicated on different servers, and you can access your data from any one of the servers and work on it that way. Well, that's great because now you get more availability. You probably get some performance increase because you're distributing the load onto multiple servers. But the huge issue that you get now is inconsistency, the potential for more inconsistency. And as you read in Grapevine, what's one of the trade-offs to trying to make sure everything's as consistent as possible? Well, it's performance. And the other problem, one of the reasons that's a problem is, imagine if you wanted to make sure that you always had the latest version of the file before you got it. Well, one of the ways that you could do it in a Grapevine type file system is to go and poll, a majority of the hosts and say, here's the version I got locally. It's got this timestamp. Does everyone else have that? Does the majority here have it? And so the more hosts you poll, the higher the probability that you have the latest version. But that's going to take a lot of time, especially if you have congestion in your network or if some of the hosts are down, some of the network's down. So what ends up happening is you have to make trade-offs. You have to make some trade-offs that don't get you complete consistency all the time, but get you enough that makes things doable. So for in NFS, one of the things they do is they say, oh, we'll replicate read-only files, but we're not going to support replication of files that can be written. And so they get around this consistency issue by giving you a little bit, which is, they'll give you read-only files, but they don't give you the full, something a lot nicer that you probably will need. That's this. By the way, this whole idea of having transparently seeing a file as just that's replicated as just being one. It's called one-copy semantics. There's only one copy, even though it's replicated amongst multiple servers. So let's think about a system that tries to give you a bit more than NFS, which is called AFS, the Andrew file system. And this is used. There's actually a lot of files that are available on the internet through AFS. And sometimes you'll get, instead of a URL, you'll get some kind of analogous type thing in AFS, which is some kind of file string. And it consists of a server, which tells you where this AFS server is, and then some path. In AFS, what you have is you can have files that are replicated, and one of the servers that has this file is called the custodian of the file. And that's the one that's in charge of coordinating, of doing consistency checks and doing a bunch of other things, which we'll get into right now. So the custodian is in charge of this file, and the idea is that unlike NFS, where when you ask for a piece of a file, you'll get a piece of a file, in AFS, you have more of the notion of you checking out a file. So when you access a file, instead of getting a piece of it, you get the whole thing. So when you go into a file, its custodian keeps track of who has that file checked out. And you can have multiple people, multiple clients have the same file. Let's give it a name. Can have that same file checked out. So, and maybe they'll get it from somewhere else. Great, so now we have some amount of, so now we can start sharing these files. Now, one of the questions is, why would you want to share at the file level instead of at the block level, like, or the subfile level, like NFS does? What's the assumption they're making? Or assumptions? Let's think about some of them.
What do you mean the subfile?
So here, when you ask for a piece of a file, you don't get the whole file. You can get a piece. You get a piece of it. So maybe a block, maybe an 8K block, maybe a 16K block, but you don't get the whole file. Here, under AFS, when you ask for any piece of a file, you get the whole file.
It's more distributed, more discontinuous kind of.
It's a this is more distributed, but this one can be distributed. I mean, these both can be distributed widely, and they can't. I mean, they are in practice. But why do you think it would make sense? Like, under what assumptions would it make sense for you to be handing out, the whole file, even though you only asked for a little bit of it?
Are they just planning for inconsistency, that people are going to be writing to different parts of the file, and it's...
Okay, you're getting at it, which is what they're assuming here is that a couple things. One is that if you ask for a piece of the file, it's likely that you're going to be using different pieces of the file, which is one of the assumptions in read-ahead, right? The reason in read-ahead caching is nice is because if you ask for one piece, it's likely that you're going to be using a lot of pieces in front of it. What they're assuming here is that if you ask for a file, it's likely you're going to be using all of it or most of it, and if you're writing to it, you're going to be writing to different pieces of it. When is that generally, like, what kind of activities is that assumption valid for? Text editing, right? You're going to be going back and forth all over that file, and so now the whole thing is there. You have a local copy which you can cache you can put right onto your hard drive, and it can be manipulated the same way using the same caching mechanisms as before. Write ahead, read ahead, write behind, all that stuff. and you've got the whole thing. And what other assumption does that make about files?
Small enough to fit.
That they're
It's not a huge database.
that they're not huge, right? And because if you're trying to do something like a 20 megabyte file and you just want the first record of it, then this will give you much better performance than this. This will be horrible performance if every time you want to read 1% of a file of a huge file, you get the whole thing all the time. Yes.
Are they pretty much assuming text files? Like, can you run a database?
So a database would probably give you, depending on how much of it you were reading and writing. If you're reading and writing a small piece of it, you'd be getting horrible performance over here compared to over here. Right? If you actually wanted to suck down the whole database file, like let's say an access file, and you wanted to manipulate, you want to do lots of reads and lots of queries, then this one would probably give you better performance because you'll always have that whole file locally. Whereas over here, when you read pieces of that file, the client, you're caching those pieces in the client's cache, and they may be getting thrown out at some point.
But it seems like that would actually magnify inconsistency problems with something like a database where you can have more than one person working on it at the time.
Yeah. So that's the next thing that I want to talk about is consistency over here. Do you have a question first?
It's just hard for me to imagine how you access subfiles. I mean, for example, say you access quiz 1 remotely. How do you specify a piece within quiz 1 to show up on?
Oh, well, over here, like suppose that you can ask for records in a file. So you can say I want the first 8K records or blocks or bytes or something like that of this file, and read that in using remember the Unix paper where there was like the read command, the seek and read. You can seek and then read and grab a block and suck that out. And you might modify it because that might be based on what the file is. There might be some data there you want to change or look at. And so if you do that over here, you'll get, and you say seek and then give me that piece, you'll get just that piece basically, or maybe a little bit of read ahead. Over here, before you can do anything with the file, it all has to get sucked in, and you have to have a local copy, and it'll be a local copy on disk. Yes.
So presumably all of this is happening transparently to the end user within their application.
That's right.
Which is how you could just suck out a little bit of it.
That's right. That's right. So if the application calls for the whole thing, then in this case, you'll get the whole thing sucked over, right? But the one key difference is even if you're sucking the whole thing over, in this case here, the file gets put, when you check out a file, it gets put onto your local drive. So you have that file. It's there on your hard drive. Over here, it gets put into the file cache. So guess what? If other things get into that file cache, things can get knocked out, and then you have to go back and get them. And that's more like what standard Unix does. Is you have a file cache, you have a file system. Things can go in and out of that cache depending on how you use them, or LRU, whatever algorithm you're using. But over here, it's there. It's on your local drive. The whole thing is on your local drive.
So it does seem as though or NFS rather, assumes much tighter connectivity between the client and the server.
Yeah, NFS is more of it feels like a lot more of just a way of having taking the Unix file system as it stands and extending it so that the bits can be on some other machine, but it doesn't do much else beyond that. Right. In terms of trying to optimize for certain situations. So you can imagine if you've got a room of coders, and they've all got small files, they're all working on small files, all right, and you have a file server. Well, what this over here gets you is that the files get sucked over locally, and then people can work on them. What this over here does is you might actually be hitting the file server a lot more because depending on how big your file cache is on each of your local machines. Okay, so what about consistency? Well, what happens is that the custodian, it keeps track of where this file has gone, to which clients it's gone. Now suppose that one client makes a change to the file. What that client then has to do is tell the custodian that this file has been changed. And what the custodian does is it notifies the other clients and tells them there's been a change to this file. So your copy that you have is now invalid. And what will happen is, say you're running Emacs and someone else makes a change, then that's something that Emacs can detect. It can say, oh no, somebody else is out there, came in and made a change, and now my custodian has told me that my local file is now not valid anymore. And to decrease the incidence of inconsistencies, each client has to check every T seconds whether it's the current version of the file that it has is the most recent valid version. So what this does is, as long as you're outside of that T-second window, you can be sure that, like when you're making writes, that you'll have the most updated copy. But within that window, within those T-seconds, it's possible that someone else can make a change that you haven't detected yet. So again, here we have the trade. I mean, you don't have the perfect situation of consistency because you can't because it's the performance for having perfect consistency degrades as T goes down, T gets closer to 0. But you do have some parameter that you can set that can be adjusted depending on the situation and the specifics of where you're installing this. Okay, does that make sense? Okay.
What's the acronym AFS?
Andrew file system? Andrew, yeah. Who is it? CMU guys, I believe.
Andrew might be Carnegie's.
Oh, Carnegie, yeah.
First name.
Andrew is Carnegie's first name. Okay, makes sense then.
It is required to update.
Well, what happens if someone else makes a change is that your client will then be told that its local copy is invalid. So that an application can handle that in a number of ways. Emacs will tell you, if someone's made a change to this file, do you still want to continue editing? So you can see that AFS gives you some performance trade-offs depending on the assumptions being made about how people are using files and the size of files. And there's a whole list of these assumptions in the book, actually, that AFS makes. I'm just covering ones that are more tightly associated with the caching model. The key thing here about distributed storage, you can read more about AFS in the book and NFS. There's a paper on a distributed file system called Echo that you guys are going to read. And when you're looking at these distributed file systems, this is one of the key things that you need to look at is what is its caching strategy, and what does that imply about consistency? Because that's the hard part. That's the really hard thing about these. And so when someone asks you to design one of these or to recommend one of these, that's one of the key places that you need to look at to make your decision. And what's going to happen is you're going to have to make a list of assumptions as to why you want to use one or the other. If you want to use something like Grapevine, which is much more fussy about consistency, there's a trade-off, and if that trade-off isn't going to hurt the particulars of where you're recommending it for, where you're designing it for, then that's great. But if it is, then so this is we're getting to one of these points where there is there is no right answer, so to speak. The right answer has trade-off. There's always a trade-off to be made, and the key here is the distribution of the file system, as opposed to other pieces like security, which we've seen ways to handle that. Yes.
Maybe I'm confused here. It seems to me that the custodian, by sending out notifications, and the client, by checking every T seconds, are essentially doing the same thing.
It's the same operation. I don't remember actually if it's the custodian that sends it out or if it's the client that sends out the request. But that communication has to happen every T seconds.
Sort of one or the
Yeah.
other.
Yeah.
And if you had a system where you have the clients doing lots of reads but no writes, the custodian could sort of get overwhelmed with having to send out lots of requests in the rare event that a system file gets changed.
Yeah, I mean, it depends on how frequently a file gets changed and what this T parameter is. If the T parameter is in the minutes, then it might not be as bad, but it also depends on how many files that custodian is managing. But that's why you can have replication also to help manage that, because the custodian has to keep all these things consistent. Now there's papers out there that you can read it where people have written about both of these, and about different ways to enhance them and improve them. And so the book covers them at one level, and if you're interested in seeing, what the latest stuff is, the latest AFS version is, and what it does to get around the latest set of issues, then you can probably do a Google search and find some of this stuff pretty easily. Yes?
Does it, if the client makes a change in the file, does it immediately send back the change to the
It sends back a notification. At the very least, the minimum thing that it has to do is say, I've changed this file, so that other people can invalidate, so that other clients' versions can be notified. Other clients can be notified as soon as possible that their version is invalid. Now, it may be the case that the client doesn't care, because imagine if you read in a file and you just don't ever use it again, right? Then that invalidation is something that you're never going to want to read that file in if you're never going to use it after that. So if you use the file once, made some change, and then saved it, but it's still stored here, eventually it'll get cleaned out, but you don't have to reread the whole file unless it's required by a process running.
This is not a good system for people to be working on shared files constantly.
Yeah, so when you're working on shared files constantly, what you do is you build. There's systems at layers above this that will manage that. One is called CVS. Someone mentioned CVS? Yeah, CVS. Pardon?
We've used it.
Okay, you've used it. So you know that it handles merging in a sense. It handles check-in, like actual check-in, check-out. So that you have that layer above that manages that kind of sharing. There's one of the things that CVS doesn't have is the notion of sort of transactions. So you can't have you can have two people checking out a file, right? And if one changes them, then the other person won't know that change has happened until this thing is checked back, until it's checked back in. A tighter system might say, well, when one person changes it, then everyone else gets immediately notified. Right, and if that's something that AFS does, that could be pulled out into CVS if you wanted.
People who are notified, all they can do is reread the file. Right?
Or you can try to merge. Like CVS has a merge function. It tries to do an intelligent merge. But merging is something that it's what I call AI complete, which means that if you could write a program that knew exactly how to merge two files together, you'd in essence solve the AI problem. Because so don't put that down as one of your projects.